Hello students, today's session is about velocity and speed with respect to two-dimensional and three-dimensional motion. In the previous class, we have seen the difference between distance and displacement and how we can represent and how we can calculate distance and displacement in a two-dimensional and a three-dimensional motion. Today's session is about velocity and speed for three-dimensional and two-dimensional. So let's proceed. So what is the definition of velocity? Velocity. If we consider average velocity, V average, then we know by definition average velocity is the change in displacement, change in position, right? Displacement by time. And we know for two dimensional, in the two dimensional motion, displacement is given by delta r divided by delta time for time. So now we know that delta r is represented by delta x I cap plus delta y j cap. Before watching this video, please make sure that you see how to represent position of a two-dimensional motion and three-dimensional motion before continuing to watch this particular session, because that is the basis to continue into velocity and speed. It's divided by delta t. Now if we consider the particle in a three-dimensional, in the three-dimensional you will have three axes, y, x and z. So average velocity will be still delta r by delta t, which will now have another component. This is for two dimensional. This will be three dimensional. Delta x I cap plus delta y j cap plus delta z k cap divided by delta t. This is for three dimensional. Right? So now we can represent average velocity. Let me take a clean slate. If you have noted down this, let us take a clean slate now. Average velocity, V average, is given by delta x I cap plus delta y j cap plus delta z k cap divided by delta t. This can also be written as delta x by delta t I cap plus delta y by delta t j cap. If it was two dimensional, you would have had just these two components, I cap and j cap. And if it is three dimensional, you will have the third component, which is z as well, k cap. So now we see we can write this as average velocity, the change in the x-axis divided by time will give the average velocity in the x-axis I cap, and this will be the average velocity in the y-axis j cap plus average velocity in the z-axis k cap. So now you can see that the average velocity in each axis is independent of each other, and it is also hence the average velocity in the particular motion is a vector sum of the average velocity on each of the axes. Hope I'm clear. Average velocity is a vector sum on each of the axes. Is a vector sum on each of the axes. Okay. I hope till here it is clear enough. So if you may permit me, I will clear this slate and proceed to the next part, that is average speed. So if you have noted it down, let me proceed to the next part. I'll clear this now. Now we'll talk about average speed. By definition, from kinematics, we know that average speed, this is not August, this is average speed. Looks like August. Average speed is equal to distance by time. Average speed is distance by time. So this has no relation with the components of y, x, or z. There is no relation. So average speed is directly the change of distance, that means the total distance, not change, the total distance traversed divided by the time. Now that we have seen average speed and we have seen average velocity, let us talk about instantaneous velocity. Instantaneous velocity is given by the tangent on the graph. If we have the motion of the particle in a particular fashion, then the instantaneous velocity is given by drawing the tangent at that particular instant. So we know that for instantaneous velocity, the time period has to shrink. So delta t tends to 0. That is when we get instantaneous velocity. So for this shrunk time period, we know the change in displacement delta x will also be small. So we can say that delta x is represented by dr, right? Actually, delta r, right? Delta x is the notation of one dimension, and the notation of two dimension and three dimension is delta r. In most of our textbook, we use delta r for two dimensional and three dimensional. This is for one dimension. Okay, so which is very small. Delta r is very small. So we can say delta r is equivalent to dr, which is very small, and delta t is dt. So instant velocity, I'll call it for now, is given by small change in displacement divided by the small change in time. So we can represent dr by dt as a projection on the x and y axis, so which can be given as small change on the x axis I cap plus small change in the y axis j cap divided by dt. This is x, this is y. So to get t, we need to represent y with respect to t and x with respect to t so that we can get individual graphs separately. So, so instantaneous velocity, v instant, can be represented as dx by dt. I can separate it out. Dx by dt I cap plus dy by dt j cap. And if it was supposed to be three dimensional, then I would have had one more component called as dz by dt k cap. Okay, this is the additional if there is a if it is a 3D, and this much is for 2D. So we can see that instantaneous velocity is the sum of the instantaneous velocity on each of the one dimensional axis. This is x-axis is one dimensional, y-axis is one dimensional, z-axis is another one dimensional. So the projection, that means the instantaneous velocity on the x, instantaneous velocity on y, plus instantaneous velocity on z will give you the instantaneous velocity of the 3D or the 2D motion. This is v instant on x I cap plus v instant on y j cap plus v instant on z k cap. So I hope this is clear enough. So let us summarize. Let us summarize. Samurai. Summarize. Let us summarize. Okay, master. Let's get serious on physics. Oh, let's physics is fun. Okay, summarize for this is for velocity. We have seen how to represent average velocity, and then we have also seen how to represent instant velocity, instantaneous. I'm writing the short form here. Please pardon me. This is average, AVG. Okay, average velocity, instantaneous velocity. Average velocity is given by average velocity on each of the axis. Right? We can write it as average velocity in x I cap plus average velocity in j cap, that means obviously it is y, plus average velocity in k cap, that means it is z. So instantaneous velocity will be similar. Instead of average, it will be v instant on x I cap plus v instant on y j cap plus v instant on z k cap. Then we saw about perform velocity, we saw speed. Speed doesn't depend on the axis. It is directly given by total distance by time. We also saw that this can be expanded as V average can be expanded as average velocity in the x component will be delta x by delta t